Gaspar, originario del Belgio, l'altro Belgio, come francofono, la parte francofona del Belgio. Gli do subito la mia email, così io rispondo volentieri, sto tempo a qualsiasi domanda, quesito, curiosità, che riguarda un po' la fisica. No, quello in inglese. Canta è il nome latino di Cambridge, University of Cambridge, Cambridge in latino, accademicamente. Dunque mi sono laureato in fisica, sono un fisico teorico piuttosto sulla teoria, infatti il dottorato di ricerca l'ho fatto in cosmologia, della quale arriveremo a dire qualcosa, perché uno dei pilastri della cosmologia è questa cosa che si chiama relatività generale. Il dottorato di ricerca l'ho fatto all'Università di Cambridge, cioè Department of Applied Mathematics and Theoretical Physics, Center of Mathematical Sciences, University of Cambridge, United Kingdom, nel dipartimento nel gruppo di Theoretical Cosmology and High Energy Physics. Sapete bene che l'ex direttore è deceduto, è Stephen Hawking, fino a poco fa, anche a 76 anni, regolarmente veniva a lavorare. Ok? Beh, questo sono io in poco parole. Volevi aggiungere qualcosa, qualcos'altro?
Direi no.
Ok. Facciamo 2 ore adesso, dalle 9 alle
10:50.
Sì. Fatemi un cenno perché non ho né orologi né niente. Ok? Bene. Allora, in inglese. Mi sono chiesto di farlo in inglese, poi if you have any questions, please don't hesitate. Just raise your hand and ask questions. I have no problems. I hope I will have no problems answering any questions you might have. Right, so let us start then. Well, thank you for inviting me, first of all. I'm very pleased to be for the second time, I think, or third or second time here somewhere. Right, so general relativity is the theme. Einstein's theory of general relativity. So before starting to speak and to explain things in general relativity, it would be useful, I think, for me to go back a little bit and say something about special relativity, Einstein's special theory of relativity, relatività ristretta o speciale, special relativity. This is a very important part of cosmology. I mean, the interesting stuff here is gravity, so relativity and gravitation. Right. So, general relativity is a relativistic theory of gravitation. Right? It's something that says, it's a theory which describes gravitation in a way which is consistent with the principles of relativity. That is the aim, that is the physical content of that theory. And, okay, this is very important for a thing called cosmology, or theoretical astrophysics. Cosmology. Cosmologia. Cosmology, right? Good, yes. cosmology is that part of physics which tries to understand the evolution and the origin of the universe. My PhD research was on cosmology, right? Theoretical cosmology. I'll tell you more about that, of course, in a while. Today, of course, it's just the first lecture that I'm going to, so we should start with the foundations, with the basic things, the special relativity. I will use simple notations like this: GR, general relativity; SR, special relativity; quantum mechanics, QM; quantum field theory, QFT. Okay, notations. Good. Have you been studying special relativity already? Yes. Okay, it's a good thing. So I'm not going to pull out everything in special relativity. I will highlight, I think, a few aspects that are very important for general relativity and for cosmology. Things like the space-time interval, the causal structure of space-time, that is very important to understand. The light cone structure of space-time. So what is it all about? Let me just go back a little bit then. What is the origin of special relativity? How did this all came about, roughly speaking, in the mind or in the way Albert Einstein, for instance, thought about it? What is the origin?
Potete rispondere anche in italiano.
Sì. Well, it's just, I think about electromagnetism and the Maxwell field equations. Maxwell field equations, these things are Maxwell field equations, okay, right? M and E. What is the fundamental message of these Maxwell field equations in the light of special relativity? I mean, what comes out of that? Well, these equations, they have 4 differential equations, integral differential equations. Something like this. You can write them in many ways. Time. Don't worry about the mathematics, I just wanted to show you one thing. So then we have the divergence of D, that is density charge, and then divergence of B is 0. H and D are related to electric and magnetic fields, right? So, yeah, D is displacement field. If you are in vacuum, you have a constant here. This is what I wanted to say. These equations, you have constant quantities, epsilon naught, epsilon 0. You know that is the electric constant vacuum, if you are in vacuum. And then you have B equals mu naught H. Epsilon naught and mu naught. Well, in a big word, you have here speed, isn't it? Something like that. The fundamental speed comes out of these equations, the speed of light in vacuum. This is a very important fact because for the first time in physics you have a physical theory which describes electromagnetic phenomena, electromagnetic interactions, and for the first time in physics you have a finite value of a speed. In Newtonian physics, in Newtonian theory for gravitation, you don't have finite or limiting speeds. And above all, you see that this speed depends on constants. this has a constant value. It's not a function of, I don't know, t, x, y, z. This means that it seems to suggest, and indeed it corresponds to the fact that the speed of light must be the same for all observers, what we have been studying. It's an absolute constant. This is already, sorry, this is already present in these equations, in these Maxwell equations. The structure, the basic structure of space-time, this was the one inside of Albert Einstein, is already hidden in these equations. Yeah? So constancy of the speed of light, this is all very simple, very, very profound, very deep thing. Absolute constant, right? Which is very strange, of course, from the perspective of Galilean and Newtonian physics. If you move with respect to a light ray, you would expect to compose, to use the composition law of velocities, yeah? And you would have a different value of the measured speed of light in different reference frames. So, the constancy of the speed of light and other properties which I will mention to you are in conflict with this Galilean kinematics. Let me just tell you something about that too. Do you know what Galilean kinematics is? Do you know what a coordinate transformation is? La trasformazione di coordinate alla Galilei, cioè Galilean, Newtonian. If you have a reference frame, a simple reference frame, okay, Cartesian reference frame. Right. And you want to study, you want to define, you want to describe the position of a point, for instance a point particle, with respect to that frame. You will have to give three numbers, the three space coordinates, x, y, and z, and an instant of time. Yes? T. Now we can imagine, as probably you have seen somewhere, that another frame can be moving uniformly with respect to this frame O, let us say, called the origin O prime. And you can, for simplicity, assume that the translation happens, motion happens and occurs only in the x direction. Okay? So you have z primed, you have y primed, x prime if you want. And you can imagine that you have a uniform speed, v or u, whatever. The relative speed between O prime with respect to O, okay? This means that you can say where P is also with respect to O primed. Okay? These are the coordinates of P with respect to O. But then you can tell someone where P is with respect to O prime. That means that you have to give new coordinates, x primed, y primed eventually, z primed, and you know that in Galilean and Newtonian kinematics, time is universal, okay? So it's always t, it's the same t, right? Now the x coordinates, you see that your x distance here from O, this is x primed, so you have to subtract a certain distance, so this is why x prime is x, okay, minus this bit, you get x prime, so x minus b times a certain time t, okay, x prime, y prime, z prime, are not changing because the translation is only in the x direction, and then t prime equals t. Okay. These are the Galilean-Claude transformations. Yeah? They seem very, very, very logical, very simple. But there's a big problem with that. Now, since time is absolute, you can divide this equation here, the left-hand side and the right-hand side, you can divide this by t, right? So you have x prime over t equals x over t minus b over bt over t, right? Dividendo destra a sinistra con t. This is the speed with respect to O prime, always, I don't know, prime. This is the speed of an object if you have a distance x over time. This can be, okay, another speed, call it u, okay, minus v. So this is the classical, well-known law of composition of velocities, right? La composizione delle velocità. The problem is that if you suppose that this x over t is described by a light ray, come un raggio di luce, this would imply that you have a c primed with respect to O prime, which is not equal to c, but c minus or plus v, depending on the direction. Okay. Right? So this is certainly not consistent with the fact that the speed of light in vacuum has to be a constant, an absolute constant. You remember that? But there is a very, very big problem as well with this. If you think about the Maxwell field equations, I don't know if you've ever seen that, but you can state it like this. I can change this. You can write like I've been doing here, right? The Maxwell field equations with respect to frame O, right? You can also write Maxwell field equations with respect to frame O primed. Okay? And how do you do that mathematically? Well, here you use t, and in here you have x, y, z. So you have to change, you have to substitute in here, and I won't do it mathematically. Change x, y, z into x prime, y prime, z prime, then you see what happens. And what happens is this, is that the Maxwell field equations are not the Maxwell field equations anymore, I mean they are other equations. So they are not, we say in relativity, they are not invariant. They change form. In particular, this relative speed does not cancel, it remains around their equations. And therefore, you have a situation where you change mathematically reference frame, reference system. You go from O to O prime using this, and you have a form, the form of the laws of nature which change, which are changing, which depend on the relative system. So the Maxwell field equations, the form of the Maxwell field equations is not invariant under the action, we say, of these coordinate transformations. I'm just bringing you to the fact that this transformation, this coordinate transformation, leads to a problem with another fundamental axiom and postulate of special relativity, which you have been seeing, i.e. the principle of relativity. Okay? Il principio di relatività in Italian. So indeed, special relativity is assuming certainly that C is a constant with respect to WRT, right? With respect to all inertial reference frames. And then you have a second postulate which goes back to Galileo Galilei, okay, the relativity principle in mechanics. I think you have been seen this. This is very important. Relativity principle. Il principio di relatività. And the relativity principle just states that the form of the laws of nature do not change when you switch, when you go from one inertial reference frame to another inertial reference frame. So if you write down the Maxwell field equations, or if you do physics with respect to O, and you look what happens with respect to O prime, you should have the same laws of physics. But if you use these coordinate transformations to go from one frame to another frame, the form of the law changes. Disastrous. Okay? You know this, okay? You know what this implies. This means that you cannot have the concept of absolute motion. You know what the speed is of our planet now, roughly? The average speed, orbital speed, tangential speed of the Earth around the Sun in space? Roughly. Good? It's about 30 kilometers in 1 second. Now, in space. You know how many kilometers this is per hour? Roughly. Multiplied by 3,600 up and down, no? So roughly this is about a bit less than 120,000 kilometers per hour. Our planet is moving with respect to the rest of the universe with that crazy speed. It's crazy, isn't it? And we are all okay here. We don't. You drink your coffee, you pour water. Everything seems to be quite normally happening. And this is because of the relativity principle, of course, because you cannot establish motion from within the reference frame. You can do, if it is a perfectly inertial reference frame, of course. You know that the Earth really moves through space only when you look at the stars. When you receive information from outside the system. But if you do experiments here on Earth, it would be exactly the same physics that would be observed and measured when the Earth would be standing perfectly still, like in the Aristotelian Ptolemaic vision of the universe. I mean, perfectly still at the center of the universe. This is the implication of the relativity principle. But of course now, this sort of physics is saying, look, the Maxwell field equations at rest, and the Maxwell field equations in a frame which is uniformly moving and with rectilinear trajectory, of course, that changes the physics. You should not have the same results, which is, of course, a contradiction. You know that many people have been thinking about all these problems more or less interconnected. There is the Michelson-Morley experiment and its negative result, which indeed seems to suggest that there is no motion of the Earth through a hypothetical ether, blah, 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 and the whole story. That the speed of light is mysteriously absolutely constant. It doesn't depend on your state of motion. It's crazy, but it's like that. Henri Poincaré, have you heard about that name? Great French mathematician, has been thinking about this. And then Lorentz and Fitzgerald. Lorentz is Anton Lorentz. So by the way, these are the two fundamental axioms of special relativity, so you are here. Lorentz has been studying all these problems. Fitzgerald Anton Lorentz in Leiden, Holland, the Lorentz force, also connected. Fitzgerald, I don't know how you say it exactly, he was a physicist in Dublin, in Ireland, Trinity College, Dublin. They try to explain with a sort of length contraction mechanism the negative result of the Michelson-Morley experiment. But also, they find a coordinate transformation, i.e. you change x, y, z and t to x prime, y prime, z prime and t prime, in another way, not like the Galilean coordinate transformations, in a slightly more complicated way. It looks more complicated, but it's actually not so complicated because in effect, sorry. If you go from one inertial reference frame to another inertial reference frame and you write these Maxwell field equations, and you change the Maxwell field equations using their transformation. I mean, we will call this the LF transformations. Le trasformazioni di Lorentz-Fitzgerald, non galileane. Allora Maxwell rimane Maxwell. Perfectly equal. Yeah. So the Maxwell field equations are not invariant under the action of the Galilean coordinate transformations, but amazingly they found, not Einstein, that the Lorentz field, when you do these Lorentz field transformations, the Maxwell field equations are invariant. La forma delle equazioni di campo di Maxwell è invariante, non cambia, quando utilizzi le trasformazioni di Lorentz-Fitzgerald. Cosa sono? And only Albert Einstein arrives at the understanding that all of this actually gives us a new theory about space and time. It's not a strange theory about electromagnetism and material bodies and so forth. It is the person who understands that behind the structure, mysteriously, of these Maxwell field equations, you have a new theory of space and time. What are these Lorentz-Fitzgerald transformations? Can I write them down? Yes. It looks slightly complicated, but again, it's not complicated, really. Or is it minus VT? This is the Galilean one. Now there is a correction. I will tell you what it all means. It usually is written like this. The square root of 1 minus v squared over c squared. C is the speed of light in vacuum. E is the relative speed of O prime with respect to O. Okay? Y prime is Y. Z prime is Z. But then you have, mathematically speaking, that T prime is T minus V over C squared times X over the square root. This structure. Again, same square root, 1 over the square root of 1 minus v squared over c squared. C, the speed of light in vacuum. Okay. Now, if you do this with the Maxwell field equations remains Maxwell field equations. Yes.
Scusi, perché rimangono invariate y e z e cambiano solo i...
Perché, come nel caso dell'esempio semplice che ho fatto della trasformazione galileana, questo sistema O' si muove soltanto nella direzione x. Quindi solo x cambia, se guardi la posizione di un punto P qualsiasi, vedi la sua altezza qua, in realtà non cambia e neanche la sua coordinata y in avanti. Okay? Se ti muovi solo lungo la direzione x, solo la x deve essere corretta, quindi deve fare una piccola correzione che sembra essere questa. These are the Lorentz-Fitzgerald transformations. Come va in inglese? È chiaro quello che dico? Okay, because I speak quite slowly and I hope quite clearly. Do you hear my voice quite well? I have a low voice, of course, but I can speak louder if you want. Now, the only thing I will say about this is this. Let's imagine as before that in O you have a light ray moving and describing space x in time t in O. So suppose that this is the speed of light, okay? Suppose. Suppose that, blah, blah, blah. Now, with respect to frame O primed, what would you do? Well, you have to calculate x primed over t primed. Because you see, time seems not to be absolute. This is all consistent with the relativity of simultaneity and blah 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 blah. Okay? If you do x primed over t primed, do this divided by this fraction. Yeah? The square root goes away. You understand that? So this result will be, will ultimately be v squared s. Because here 1 over the square root, 1 over the square root, this simplifies out of the fraction. And so what happens? You divide numerator and denominator by t, or then pull it out as a factor, equivalent. Minus b over c squared times x over t, right? But this is c. So this t goes away, ciao. X over t is c, good. 1 minus b over c. Because you have a factor here, ciao. This is, if you put c as denominator, right, c minus b over, okay, c minus b over c. This is c. So this term has become c, it's exactly the same speed. So the Lorentz-Fitzgerald transformations are strange, but they are guaranteeing us that the speed of light has always this strange absolute value. This is why the correct space-time transformations are the Lorentz-Fitzgerald transformations. Right. Then you have been studying length contraction and time dilation. Yes?
Yes.
So duration and length are relative. An instant of time is relative. Simultaneity is relative. Even the measurement of length is relative. Indeed, this can also be shown quite easily from the Lorentz-Fitzgerald transformations. you can deduce from these transformations that you have length contraction, you have time dilation. Yeah? Dilatazione delle durate, contrazione delle durate, sono conseguenze, si intravede già nelle trasformazioni LF, no? Sono differenze tra x1 e x2. Okay, ma queste sono, these are things that you have already been seeing. So I wanted to arrive at something magnificent. Okay? The news is that in special relativity, time is relative, space, length is relative, but there is a way to combine time intervals and space intervals such that that quantity is absolute as well. So in this theory there is another absolute invariant quantity apart from the speed of light. It is called the space-time interval. And this is due to Minkowski. Minkowski space-time it's called. It will be called Minkowski space-time. And Minkowski was a geometry, a mathematics professor in Switzerland, and he was a professor of young Albert Einstein. They didn't get on very well. Einstein didn't follow any of his lectures, or few of them. However, after some time, when Einstein's theory became more famous, Minkowski had a very interesting, beautiful idea. Time on its own is relative, space on its own is relative, in special relativity, but if you combine them in a certain way, which I will show now, you probably know that, but then it's useful to deduce something out of that. If you combine it in a certain way, you get an invariant absolute quantity, which is called the space-time interval. Space-time interval. And this is why in physics we don't speak about space and time, like in Galilean or Newtonian physics or dynamics, but about space-time. This is why this word is important. And in general relativity, the structure of space-time is absolutely fundamental. This is why I'm explaining these things. Yeah. Now, what did Hermann Minkowski note? Again, this is a simple, simplified, two-dimensional space-time diagram, just a spatial dimension and a time dimension. Space, time. I will use c times t in the vertical axis. Okay. Why? Well, one reason is simple physical common sense. I mean, if you want to combine in a simple expression a distance, x is a distance, it's space dimension, and time, you can't. I mean, you have to combine time with time or space with space. I mean, from the unit of measurement perspective, you cannot combine apples and bananas, okay? You must combine meters. This is meter, speed multiplied by time, and this is in meters. So this should be okay to construct a simple combination, linear combination. So how does it work? Imagine you have an event in space-time. Remember this word, keep it in your brain. In space-time you don't have just points, we don't speak just of points of space-time, we speak about events. So somewhere something can happen also. So this is the concept of event. So you have an event in A. That means somewhere, coordinate, the coordinate here is XA, somewhere something is happening, and eventually somewhere else in B, something else is happening. This can be X. And what happens in A happens in TA, was observed in TA. And what happens in B is observed at instant of time TD. Right? This means that two events in space-time have a spatial separation, but they also have a time or time-like separation. It's simply the fact that this is the space separation, right? A delta x, which is just xb minus xa, obviously, in this simple case. And you also have a time separation. And this time separation is c times, okay, a delta t. tb minus ta, the difference. Well, you obviously all have an irresistible temptation here, isn't it? Pythagoras. You would like to say that the effective space-time separation between two events is the hypotenuse of this rectangular structure, triangle. And if you call this, I don't know, delta S, then in flat space-time like this, you have Pythagoras, so the square of the hypotenuse is just the square, sorry, the sum of the squares of the two other sides. So it's an inverse. Now this is not Minkowski's space-time interval. But the true space-time interval is almost equal to that. There's a small difference, but it's a fundamental difference, an immensely important difference. The fact is that, again, this is calculated with respect to frame O. But in relativity, you want to see, you're looking for absolute things, eventually. So you might do the same job with respect to O prime. I'm simplifying a little bit of thinking. Okay, but however, you know that the correct space-time transformations are not the Galilean one, but the Lorentz-Fitiron one, the LF. Now, if you change this expression using the LF transformation, then you would have delta S primes here, as opposed to the delta S, yes? But if you use these transformations with this quantity, you get delta S primed squared, for instance, not equal to delta S. So this kind of combination between time interval and space interval is not invariant with respect to the Lorentz-Fitiron transformation. So no absolute quantity. But Minkowski sees that simply by changing this expression to this one, with a minus in front of this term, or equivalently, you can also construct another one. It doesn't matter. Not pluses, but at least one minus somewhere as a coefficient. I prefer this one, that's just a convention. If you have a minus in front of one of the terms, at least one, okay, in this case, in front of the time interval sort of term, then a mathematical miracle happens. Simply because of this minus sign, if you do the LF transformations, then it is easy to show and delta S squared is perfectly equal to delta S prime. And this space-time interval is absolute. Not that one. If you really deeply love Pythagoras, if you still want to do it in a Pythagoras way, you know that mathematically, if you put here, if you really insist, I, C, T, I is the imaginary unit, I mean, common times I squared equals minus 1. Then you can do Pythagoras to get a minus there, I squared, with the difference would correspond to I, C, T. And so the square of it will be I squared, C delta T squared, delta X squared. I squared equals minus 1.
Io, secondo me è il caso, credo, di fermarsi un attimo. Come sistema di state seguendo? Sì. Avete capito il perché del meno? Chi crede che no? Ok.
Lo faccio vedere in un attimo.
Sì, infatti è meglio secondo me. Ascolta un'altra cosa ragazzi, noi in realtà i numeri complessi non li abbiamo mai visti.
No, ma sono commenti.
Esatto, l'unica cosa da sapere è la relazione che Yves ha scritto qua. Si immagina questo numero immaginario, per cui il nome I, tale per cui se lo si eleva al quadrato il risultato fa meno 1, va bene? Ok?
Non è un numero reale, chiaramente che non esiste una quantità reale tale che elevato al quadrato sia meno. Ma sapete che i matematici vanno avanti, inventiamo un nuovo tipo di numero non reale ma immaginario, un numero immaginario ma complesso. Poi andare avanti a fare calcoli. Tutta l'analisi matematica che state studiando adesso si può formulare sulle variabili reali ma anche con le variabili immaginarie. Si chiama complex calculus. Cosa dunque? Ancora una volta, fate di solito un intervallo, forse?
Dipende. A volte sì, a volte no. Come vuoi tu, insomma.
No, volevo far vedere forse che
sì.
Delta S squared scriviamo senza il delta, ok? Nel senso che delta t è in t meno 0, supponiamo che l'istante sia messo a 0, ma delta x è x meno 0, ok? È x stesso. In altre parole, mettiamo uno dei due punti, let's put one of the points at the origin. And then you look at the Lorentz-Fitzgerald transformation. So you want to show that this is equal to this. Time is relative, so if you go from O to O primed, sorry. If you go from O to O primed, okay, se cambi il sistema di riferimento, questo intervallo, questa strana combinazione col meno, adesso ho messo meno là, scusate, prima avevo messo convenzione quella, devo dimostrare che quando metti qui al posto di t' l'espressione delle trasformazioni di Lorentz-Fitzgerald e x', trasformazione di Lorentz-Fitzgerald, avete proprio l'uguale. Questo è esattamente uguale. Se lo fate con più, questa roba cambia. È più chiaro adesso? Volete che vi faccia la dimostrazione? È algebra, è un po' tedious. Esempio. Subito, il calcolo di questo lo potete fare un esercizio.
No, potremmo fare così, lo fanno per esercizio e lo connettiamo.
Sì, vi dico come si fa.
Sì.
1 fratto gamma is equal to 1 over the square root of 1 minus. Okay, Lorentz physical right. And t primed squared is the square of, okay, gamma squared the square of t minus l'espressione trovata delle trasformazioni di Lorentz. E fate la stessa cosa per x prime, dunque più che dice un gamma seconda x meno per t alla seconda. Ok? Dopo a un certo punto dovrete sostituire comunque gamma square con il suo valore, con la sua espressione. Beh, voi fate i quadratini anche raccogliete gamma alla seconda in caso, ok? Gamma square ed è esattamente uguale alla fine a questo. E vedete con i termini che ci interessano, cioè minus c square t square minus x plus x square. È un'espressione assoluta, absolute quantity. So you can do it as an exercise. Now, this is the very important information we have here. Minkowski spacetime. The invariance of delta S squared is related to a very interesting concept which is called, which you can call the causal structure of space-time, la struttura causale dello spazio-tempo. Alla fine, in the end, the finite value of the speed of light, okay, imposes limits on causality, and therefore you can speak about horizons in space-time, space-time horizons. So this is related to the causal structure of space-time. Okay? And this is very important because this will become very important, especially in general relativity and in cosmology. And in black hole physics, if you're curious, and you will read more and more and more, space-time horizons, the concept of horizon is extremely important. It's part of modern physics. There is a concept of horizon. We all have to do with space-time horizons, and they are defined by the value of the speed of light. The finite value of the speed of light. You know that from all the equations of special relativity, nothing can have a speed greater than the speed of light. The speed of light is an upper limit. Let me just explain a few things here. So, look at this. Right? Now imagine that, sorry, I'll do the simple drawing. Imagine that from A to B, okay, in space-time, a light signal is traveling, a light ray. Yes? We look always at light rays. Now, if light is traveling from A to B in space-time, this means that a light ray will travel this distance, which I have called here delta x. But if this spatial distance, okay, so to speak, is described by a light ray, this means that in that time, in this time here, delta t, light will go from A to B. In other words, you can always say, if this is done by light, that this distance is equal to c times delta t. È spazio con la velocità per tempo. Se è la luce che te lo fa, allora delta x must be equal to speed of light multiplied by time. Yeah? What is then the value of delta s squared between two points connected by a light signal? Sostituisco qua, what happens? Sorry? Zero, yes. The space-time interval between 2 points which are connected by light ray is 0. It doesn't mean that there is no distance between A and B. It's the space, it's a new way to say that A and B are along a line in space-time connected by light. Okay? This is why in relativity this is called a null interval, intervallo nullo, or light-like interval. Light-like, light/like, intervallo di genere luce. Light-like, or null interval, null zero, intervallo spazio-temporale, nullo. Null interval. Yes? One thing at a time. So, I haven't been drawing this thing very well indeed, because you see, in a simple space-time diagram, like this, look at this equality here. If this is done by light, this means that this bit, this distance, this length, in the diagram must be equal to that length. Yeah? This means that this line must be at 45 degrees. For instance, if I simplify things, here, exactly at 45 degrees. Right? So here I have a light signal traveling to the right. But I could have a light signal, or light ray, traveling to the left. Traveling in the x and the y direction, so adding more space dimension. So the structure which is going to be designed is actually a cone. This is called the light cone in space-time. If you add the y direction, you can visualize it as well, like coning sort of thing. This is called the light cone. Cono di luce, or null cone in some texts. Okay. Can I cancel this? Can I erase this? Right, so let's write again our little interval here. It'll get more and more interesting. Okay, in the case of a light signal, delta x is equal to c times delta t. Yes? In the case of an object which is moving at a speed less than the speed of light, what happens? Well, then of course its distance typically is speed times total speed times a given time duration. So this is less. Since v is less than c, this must be less than c times t. Un oggetto che si muove a velocità inferiore, come noi nella vita quotidiana, la fisica qua, è caratterizzata da velocità molto inferiore a questa della luce. Ecco perché v fratto c, v over c is negligible with respect to 1, and apparently the Lorentz-Fitzgerald transformations look like the Galilean. Yeah? But anyway, this means that for normal objects, if the space separation is less than the time separation, you are not on the diagonal. You are not on the diagonal there, or on the light cone, because you see, if you are a light ray, then this bit, if you are 45 degrees, is always equal to this bit in the CTX diagram. Now here you have to imagine delta x less than the time bit. So this means that you are somewhere here. Okay, the space bit is smaller typically than the time bit. You are inside the light cone. That means that all bodies, material particles, which have speeds less than the speed of light, they all travel, and they have to travel inside the light cone. Indeed, if you imagine something impossible, according to Einstein's special theory of relativity, then V must be bigger than C. But if V is bigger than C, and you write this down, this means obviously that the space separation is greater than the time separation. If your speed is bigger than the speed of light. This means that you would go outside the light cone. Here, you would have an inclination greater than 45 degrees. Understand? This is one way of seeing the light cone. The light cone is a limit in space-time, this one, out of which no physical signal can get out like this. Otherwise, you would travel faster than the speed of light. Yes? Because nothing can travel faster than the speed of light, you are confined by this light cone. Yes? So the light cone, which is defined by null intervals, like light-like intervals, is a horizon, is a sort of causal horizon, as I will try to explain. Un orizzonte causale, un limite. And in general, of course, if you have space-time, I'll simplify the drawing a little bit. Light cone. If you have an angle alpha which characterizes a simple motion here, then you must have something like a tangent of alpha, the angle with respect to vertical. Tangent of alpha is the ratio of V over C. Indeed, if V is equal to C, if you are a photon, if you are a light ray, then the tangent of alpha is 1 and alpha is 45 degrees. You are on the light cone. So this, we are saying that in space-time, nello spazio-tempo, la luce viaggia sempre lungo il cono di luce. All the other phenomena and particles which have speeds less than the speed of light all travel within a light cone. And this is now the classification of space-time intervals, an abstract classification, but it's very interesting. And in general relativity, cosmology is important. You have a null cone, Now, 2 points which are on the light cone have delta S squared equals 0. 2 points inside the light cone, but in this way, have a time part greater than the space part. This means that delta S squared, this is on the light cone. Inside the light cone, okay, inside the light cone, you are more vertical. So delta S squared, which is equal to minus c squared over t squared plus delta x squared, is, if this part is greater than that part, then the result is negative. So delta S squared is negative. I know this sounds very strange, of course, the square things are negative, but this is, if you accept the existence of imaginary numbers in mathematics, this is not a problem, but anyway, this is not the point. Inside the light cone, you have negative delta S squared. And these type of intervals, which have more time than space between them, these are called time-like. If you have more space than time, you are space-like. And if you are null, if your space-time interval is exactly null, it means that you have an equal amount of time and space. This is null interval or light-like interval. This is time-like, degenerate tempo. And if you are outside the light cone, for instance, a point here and a point here, very, very much inclined, greater than 45 degrees, then this means that there's more space and time. So this is greater than this, so the result then is delta S squared, typically positive. This is space-like. Okay? Intervalli nulli o di genere luce, intervalli di genere tempo, Italian, and intervalli di genere spazio. Vuol dire matematicamente, ok, fuori dal cono di luce, sul cono di luce e dentro. This classification defines the causal structure of space-time. And the nice thing is that this classification of space-time intervals is absolute. It's not relative. Why? Because this structure here is an absolute quantity. And this is why it's so important. Right? So what does this mean practically? Example. Imagine you have somewhere in space a light bulb. La lampadina che si accende, a light bulb switched on, a light source. Luce. Okay? At a certain distance from this source, somewhere in space, you have a person, P, an observer, at point P. Question, in space-time, when will the observer be able to know something about the light source? I mean, when will the observer receive the light? Well, if this is a space-time diagram, okay, you have a time axis vertical, space axis horizontal. You have the light traveling at 45 degrees. This is the light cone. This is the light cone. I'll define it better. This is the future light cone of L, event L in space-time. When will P know about L? When is L going to be visible for P? In space-time, everything is always moving in space, but now we seem to be standing still, but we are moving in time. Time is passing. So this means that this person here, even if he is not moving along space, he is at rest with respect to a certain frame. That means that this person moves up in space-time, and here it happens. When this person enters the light cone, the future light cone L, L becomes visible for P. No, Prima. And then P can continue. P can really enter the light cone. This means that at this instant of time, this is CT, of course, this is X. At this instant of time, call this TA, this point A, when P enters the light cone, the future light cone of L, that means that P can receive something from L, know about L. Okay? Now, in relativity, we speak about also, I have seen these texts about black holes and whatever. We speak about future light cones and past light cones. So you can define these things here. CT, space. So if you have a point somewhere in space, okay? Space-time, point P. You can define the causal future of P, il futuro causale di P. Con di luce, future null code. Ok? Di solito questo insieme si chiama I più DP. Causal future. Cos'è questo? What is the causal future? It is the set of all points or events in space-time which can be causally influenced by what happens in P. Vice versa, you have the causal past of the event P, il passato causale del cono simmetrico passato. This is usually called I minus P. This is causal future. In the future, it is causal past. What is the causal past? It is this set of events or points of space-time which can influence what happens at P, at this instant of time, at the instant of time T, P. Yes? What can happen in space-time is that different points in space-time can have intersecting light cones. Our light cones, your light cone, my light cone, your light cone, your light cone, our light cones are mutually intersecting, overlapping. They have a non-empty intersection. Otherwise we wouldn't be able to see each other and to communicate. If you interact causally, it means that at least, for instance, if this is you now, okay, and this is another person, you, okay, when can we say, and where can we say, that P and Q share a common causal past in space-time? In space-time you must calculate, you must just draw the past light cone of Q, il passato di Q, the past of Q, and you see that the past of Q intersects the past of P only here, from this point onwards. Il passato di una persona può intersecare il passato di un'altra persona, di un altro oggetto. Past intersecting, come anche il loro futuro può o non può intersecare, non si interna. Ovviamente il loro può induce. Se tu vuoi dire qualcosa a qualcuno, fare qualcosa con qualcuno, sarebbe una buona cosa se i coni di luce possono intersecarsi. Tu entri nel mio cono di luce e io nel tuo. Ciao. Welcome in my life. Thank you. Welcome. This would be the correct space-time alignment. But I mean, physically speaking, and in cosmology, this is extremely important. Physics here. It means that maybe a lot of things are happening, right? Physical phenomena. Now, the given physical phenomena can causally influence P. Why? Because there is a signal traveling at less than the speed of light, less than 45 degrees with respect to vertical direction, and influences P. But the same physical phenomena here, which is an important intersection, can also influence Q, right? So, qualche cosa, in italiano, che accade più fisicamente può, il medesimo fenomeno fisico, influenzare sia P che Q. Se Q è troppo distante nello spazio, i coni non si intersecano così rapidamente, si intersecano più indietro nel tempo. Your father and your mother, my father and my mother, your father and mother, they have, of course, they are part of your causal past. Obviously, otherwise you wouldn't be here. Adesso ve ne dico una. Why is this, why do I insist on these little things? This is extremely important. Causal structure of space-time. It's going to be important if you speak about black hole space-times. Physics. I hope if you have been curious, you have been maybe reading some book about the work of Stephen Hawking, Roger Penrose, and space-time diagrams. It's all light cones, the whole bloody time, all over light cones and conformal diagrams. In fact, a black hole is a special type of light cone. I'll tell this to you in a minute. It's very, very interesting. And then you can apply topology, mathematical analysis techniques onto the causal structure of space-time and prove interesting theorems. Another extremely important thing is cosmology. Cosmology is important because and black hole as well. Black holes have a horizon. Vedrete questo. You will see this. It's called the event horizon. Again, the word event horizon. Event horizons can exist as well in cosmological space-time, even if you don't have black holes. Event horizons, another type of horizons. These are applications, right? Why it is useful to use these instruments. in order to do modern physics in this sort of contexts. And right. Between parentheses, what is a black hole roughly? We can already understand it conceptually speaking. A black hole is a region of space-time, so it's a set of events where gravitation is so strong that not even light can escape. Una regione dello spazio-tempo dove la gravità è talmente forte che, tenterò di spiegarmi, nemmeno la luce riesce a fuoriuscire. Okay? The boundary of a black hole is the event horizon. The boundary of a black hole è proprio, is the event horizon. I'm mixing Italian and the event horizon. Okay? Buco nero, frontiera del buco nero. Okay? This is the event horizon. This means that if you go towards a black hole and you are careful enough, you can go back. Okay? If you're not careful, and you touch the black hole, you enter, you touch the event horizon, then you will be inexorably absorbed by the black hole and destroyed. Okay? This is the inside, probably what we think is the inside of the black hole. Okay? But think about the boundary. The boundary is the event horizon. Okay, this means that from these points, even light cannot escape. Okay? So in fact, the event horizon in space-time is not a little, you don't have to imagine the black hole like a sphere. The correct vision is not space and time, but space-time. So in a space-time diagram, a black hole is actually a light cone, a particular light cone. Or if you have Minkowski space-time, okay, this one of the light cones here, this one for instance, this is a black hole. Why? Because if you are playing around and you don't see, you are not careful enough, and then you think, I'm traveling around, yes, that's right. If you cross the event horizon, it is the event horizon, this tree, if someone falls into the black hole like this is another person, not very careful person, gets into the black hole, and then he says, I'm feeling strong gravity here, I have to get out here, I have to get out very quickly. He can't. Why? Because in the space-time diagram, if you want to get outside the black hole, you have to do something like this. I'm exaggerating a little bit, right? You have to get out. But this means have an inclination greater than 45 degrees, so faster than light. But you can't go faster than light.